In this video, we'll learn rules for plotting the root locus diagrams. Yes, you can plot root locus of a transfer function using the MATLAB command rlocus, but it is still important to learn how to plot them by hand. That really helps in designing the controllers where you don't yet have the transfer function whose root locus you want to plot. You're supposed to decide the transfer function iteratively. Consider this block diagram. If you ignore the disturbance, you can reduce this into a single block, which is the closed loop transfer function. The closed loop transfer function is x fgk divided by 1 plus x gkh. The open loop transfer function is just x gkh in the denominator. The controller design specifications depend upon the poles and zeros and gain of the closed loop transfer function, and the root locus helps us see how the closed loop poles move as you change your controller gain by some factor x. The controller poles and the controller zeros have to be decided separately. For a simple system with no sensor dynamics and no pre-filter, i.e. a unity feedback system, single degree of freedom, as you change the controller gain by factor x, the closed loop zeros are same as the open loop zeros. They are the zeros of gk. The closed loop poles are the solutions of 1 plus xgk equal to 0. And by definition, the plot of the solutions of 1 plus x times some transfer function equal to 0 as x goes from 0 to infinity is called the root locus of that transfer function. In this case, that transfer function is gk. So root locus of gk, i.e. the root locus of open loop system, plots the path of the closed loop poles. For a more general system, as you change the controller gain by factor x, the closed loop zeros are not completely same as the open loop zeros. Instead, they are the zeros of f, gk, and the poles of h. Similarly, the closed loop poles are the solutions of 1 plus x gkh equal to 0 along with the poles of the prefilter f. Hence, they are given by the root locus of gkh and the poles of the prefilter f. Let's learn about main rules for plotting root locus of a transfer function. Please note that rlocus transfer function is actually the MATLAB command to plot the same. And usually the transfer function we choose is an open loop transfer function. It has open loop poles and open loop zeros. And then as the gain changes from 0 to infinity, we get the closed loop poles. The first rule is that when the gain factor x is 0, the closed loop poles are same as the open loop poles. And then as x increases towards infinity, the closed loop poles travel around and either reach the open loop zeros or diverge to infinity. Let's look at these two examples on the side. The crosses represent the open loop poles. These are poles of the transfer function. The O's represent the zeros, the open loop zeros. These are the zeros of the transfer function. The paths shown here as green, blue, and red are actually the path taken by the closed loop poles. If you look at the green path, it starts from a cross, i.e. open loop pole, and then as x increases, it goes to and follows a circle and eventually reaches infinity. So the closed loop pole, the green closed loop pole, starts from the open loop poles and then move around and then ultimately reaches infinity. Similarly, the blue closed loop poles, it starts from an open loop pole, it starts from an x and then moves around and then ultimately reaches an open loop zeros, i.e. a O. And the same is true for the other graph. One of the closed loop poles, the blue one, starts from the cross, i.e. an open loop pole, and then ultimately goes towards infinity. And the other closed loop pole, the green one, starts from an open loop pole, i.e. a cross, and then goes towards infinity. The third, the red closed loop pole, it starts from the open loop pole and then ultimately reaches towards an open loop zero. So that's the first rule. Second rule is that the path taken while traveling are unique. They are symmetric about the real axis and they are non-intersecting, but they can touch. And you can see that easily over here as well, that the path taken are pretty unique. You will never see an intersection between them, but the paths do touch sometimes. And for example, the green and the blue paths, they touch at that point. This place where they touch together and then move and then join together, that's called a break-in point. And this place where they touch and then they move away is called a break-off point. Also note that they are symmetric about the real axis, and the reason for that is very simple, because the complex poles, when you have imaginary part to them, always occur in conjugate pairs. So if 2 plus I is a pole, then 2 minus I is also going to be a pole, and therefore they are symmetric about the real axis. The third rule is that there is always root locus on the real axis to the left of odd number of open loop poles and open loop zeros. Let's see that. So if you notice on the real axis, there is always root locus at some points in the real axis. For example, there is no root locus over here, but yes, there is root locus between the two crosses. There is no root locus over here, but there is root locus over here and here. Here, this is to the left of nothing. This portion over here is to the left of one closed loop hole, as one open loop hole. This portion over here on the real axis is to the left of two crosses, and 2 is even, so that doesn't happen. And then this portion over here is to the left of 3 open loop poles or 3 open loop poles or open loop zeros, and 3 is odd, so that's okay. So basically, whenever you are to the left of odd number of things, and by things I mean crosses and O's, then there will be root locus on the real axis. Similarly, there is no root locus over here. This whole segment is to the left of one thing, which is odd, and therefore that exists. This whole segment is to the left of two things, the two crosses, therefore there is no root locus over here. And then this segment is to the left of three things, 2 of them are crosses, 1 of them is O, so there is root locus, 3 is odd. And then this segment is to the left of 4 things, which is even, so there is nothing over there. So this real axis rule is very useful, and then it's actually one of the first rules we try when we draw root locus diagrams. Next, so as we seen earlier, that some of the closed loop poles, they get to reach open loop 0. They start from open loop poles and reach an open loop zeros, but the remaining closed loop poles, they go towards infinity. Now these poles which go towards infinity, they go towards infinity by following some lines, and these lines are called asymptotes. For example, the green pole over here, it goes towards infinity, and it's following a particular line over here, and that's the asymptotic line. Similarly, the green pole over here, it goes towards infinity by following a vertical line, and the blue pole over here goes towards infinity by following a vertical line. These lines, the verticals and the horizontal lines, are called asymptotes. Now these are the basic rules for plotting root locus, and they are enough for us. But please remember, this is not the end of it. There are a lot more rules. For example, rules regarding the location of branching points and the break-in points and the break-off points, and also at what angle you're leaving the poles and zeros. But those are not relevant to us. At that point, we'll just use the MATLAB command rlocus. As seen before, the closed loop poles travel from the crosses and go towards the zeros or infinity. And when they go towards infinity, they go towards infinity following some special lines, and we call those asymptotic lines. The first rule is about the number of such asymptotes. And the answer is, the number of asymptotes you're going to have is number of open loop poles minus the number of open loop zeros. Consider the first example on the right. We have 2 crosses and 1 O's. So 2 minus 1 is 1, so you're only going to have one asymptote, and this is that one asymptote which the green pole follows to go towards infinity. In the second example, we have 3 crosses and 1 O, so the number of asymptotes would be 3 minus 1, i.e. 2, and we'll have 2 poles going towards infinity following those lines. So green goes towards infinity, ultimately following that vertical line, and then the blue one goes towards infinity following this downward line, so that would be the second asymptotic line. The second thing about asymptotes is that all these asymptotes, they always intersect at a special point, and we call that as the center of asymptote. And the center of asymptote has a formula. It is equal to sum of open loop holes minus sum of open loop zeros divided by n, which is the number of asymptotes, which is equal to number of open loop holes minus number of open loop zeros, as seen before. Okay, in the first example, there's only one asymptote. It does not have any intersection point. In the second example, we have two asymptotes. So let me delete this and show the asymptotes again. So in the second example, we have two asymptotes. One is this vertical line, and the other asymptote is the downward vertical line. And both these asymptotes, they intersect at a special point on the real axis, and that's it. And that's the center of asymptote. To find it, let's apply the formula. So the sum of open loop holes, well, we have three open loop holes. So the sum of open loop holes would be 0, first open loop holes, minus 1, the second open loop hole, and minus 4, the third open loop hole, minus the sum of open loop zeros, of which there is only one, and that's minus 2. Divide by number of open loop holes minus number of open loop zeros, which is the number of asymptote, and there are only two asymptotes. So if you do all that math, minus 5 plus 2 is minus 3, so minus 3 over 2 is minus 1.5, and minus 1.5 is indeed the center of these two asymptotes. Let's delete all that. So that's the second thing about asymptotes. So first thing was the number of asymptotes. Second thing is about where the asymptotes intersect. And the third thing is the angle of these asymptotes. Now the angle of these asymptotes actually depends upon the number of asymptotes, and this is a formula for it. So the angle would be plus or minus pi over n, plus or minus 3 pi over n, plus or minus 5, and so on and so forth, the odd numbers basically. Let's apply this. When n is 1, i.e. there's only one asymptote, then the angles would be plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on. But if you note very carefully, all of these are actually the same angle. Plus pi is also 180 degrees, minus pi is also minus 180 degrees, and then plus 3 pi is also the same angle, minus 3 pi is also the same angle. So all of these point to the same angle, and that is 180 degrees. And when n is 2, it's plus or minus pi over 2, plus or minus 3 pi over 2, and so on and so forth. Let's look at it. Plus pi over 2 is 90 degrees, so that's the vertical asymptote going up. Minus pi over 2 is minus 90 degrees, so that's the negative 90 degree, the downward going asymptotes. Plus 3 pi over 2 is the same downward angle. Minus 3 pi over 2 is the same upward angle, and so on and so forth. So if you look at it, all these infinite variety of angles given by the formula, they actually only point to two angles, which are the two angles of the asymptotes. And using this, we have a complete information about the asymptotes. So let's actually, apply all those angle formulae and pre-calculate the angle of the asymptotes for some special cases. As you've already seen, when n is 1, i.e. there's only one asymptote, you're going to have minus 180 degree, so that would be the angle of the asymptote. When n is 2, there are two asymptotes, and they will be at plus 90 degrees and minus 90 degrees. When n is 3, if you apply the same formula, you'll see that the angles would be plus 60 degrees, minus 60 degrees, and the 180 degrees. So those are the three asymptotes, and all the asymptotes would be intersecting at a special point, the center of asymptote, for which we have a formula. Sum of open loop holes minus sum of open loop zeros divided by number of open loop holes minus the number of open loop zeros. When n is 4, if you apply the formula, there will be four asymptotes all intersecting at one special point, and the angle of those asymptotes would be plus 45 degrees, minus 45 degrees, 135 degrees positive, and 135 degrees negative. So having these pre-calculated angles usually help us a lot. Now it is time to do examples where we shall apply all the rules which we have seen so far, and then we'll go from there. So here we have an example of a transfer function which has only two open loop holes and no open loop zeros. So according to the first rule, the closed loop holes will start from the crosses and they will go towards either infinity or 0, and then since there is no 0, so they will just go towards infinity. So we'll have two poles going towards infinity. There'll be two two asymptotes, and when you have two asymptotes, the angle of the asymptotes would be plus and minus 90 degrees. Okay, but one of the most important rules which we apply is the left and right rule. So according to the left and right rule, there is no root locus over here, but this whole segment is to the left of odd number of things, is to the left of one cross, there is root locus over here, and this segment over here is to the left of two things, so there is no root locus over here. Alright, so that's a real axis rule applied. The next rule was about, the next step we're going to do is draw our asymptotes. So since we know that there are two poles going towards infinity, so it will be two asymptotes plus or minus 90 degrees, we need to find the center of the asymptotes. For that we need to know the exact value of these poles. Let's assume this is plus 1 for time being, and let's assume this is minus 2 for time being. Then the center of asymptote sigma is going to be sum of the open loop poles, which is 1 minus 2 minus the sum of the open loop zeros, of which there are none, divided by the number of asymptotes, which is 2. So the center point of the asymptote is going to be minus 1/2. So around here. So the asymptotes will kind of go like this, plus 90 and minus 90, following this line. Alright, so what would be the root locus then? Well, we'll have two closed loop poles, and this is the only option which satisfy all the rules. Poles start from here and then go towards infinity, and the other pole starts from here and then go towards infinity following the other line. And this place where the two poles intersect each other is called the break off point, because the two branches come together, touch, and then move away. So this is how the closed loop poles will travel as we change the gain factor x from 0 to infinity. Let's do another example. In this example, we have a transfer function with two open loop poles and then two open loop zeros. In this case, we are not going to have any asymptotes because both the poles will get to go to a 0. None of them will have to go to infinity. And let's apply the first rule, which is the real axis rule. There is no root locus on this side. There is root locus to the left of odd number of things, so there is root locus on this whole segment, and there is no root locus over here. Okay, and then the closed loop poles are going to start from the crosses and go towards zeros. There are no rules regarding the asymptotes, and if you see, this is how they're going to do. One pole is going to start from here, branch off and go to a 0. The other pole is going to start from here and then branch off and go to the other 0. So that's the root locus that satisfies all the rules. Example 3 and the last example. Now let's consider a transfer function which has 1, 2, 3, 4 open loop poles and then one open loop 0. In this case, so one of the poles will get to go to a 0 and the remaining 3 poles will have to go to infinity following the asymptotes. But first, let's apply our real axis rule. So there is root locus, no root locus over here, but there will be root locus in this segment. No root locus in the next segment, but there will be root locus in this segment because that's to the left of odd number of things. Okay, so that's the real axis. Now we have 3 poles going towards infinity. Then we need to find the 3 asymptotes. The center of the asymptote would be obtained by summing all the poles, subtracting the zeros from it, divided by number of poles minus number of zeros. Let's say we do all that math and the center of asymptotes comes out to be somewhere around here. Okay, so now we know that there are going to be 3 asymptotes, and if you use the angle formula for that 3 asymptotes, the angle would be plus 60 degrees, minus 6 degrees, and then 180 degrees. So those are the 3 asymptotes. Finally, we must draw the root locus which respects the real axis rule and ultimately go towards the asymptotes as the gain goes from 0 to infinity. And here is that answer. So let me just delete some things. The first closed loop pole will start from across and then directly go towards that 0, following that real axis segment. and the other closed loop hole will start from a cross and go towards infinity like the other real axis segment. The remaining two closed loop holes will start from a cross and follow these asymptotes. First one follows this asymptote, and the other one will symmetrically follow the other asymptotes. So that's the root locus for this system. By following these four simple rules, you can draw the root locus of most simple systems. And sometimes there is some ambiguity, but you can learn by practice what's going to be the best answer and what's going to be the right answer. In reality, you just need to know an approximate way to find the root locus diagrams. If you want an exact answer, we'll always use the rlocus command in MATLAB.